Okay, I've been over some of the high points of this syllabus. We'll discuss it in more detail next time. Talked a little bit about what fields people are going into and stuff. Let's just dive into a little bit of the preliminaries. This course goes by any of three names. Calculus 3, which doesn't tell you anything. Multivariable calculus, which is calculus of functions of more than one variable. And vector calculus. Okay, just about everything we do after the first few weeks is with vectors. Okay. So, first question: how many? Has everybody had linear algebra? Anybody that hasn't? Okay. First year engineering students? Okay. Okay, so we're gonna have to spend a little time developing the ideas of vectors. You would have encountered vectors in, well, did you encounter vectors in your calculus course? You basically know what a vector is. Okay. Should have also encountered it in pre-calculus. In the pre-part. So I'm going to assume you know a little bit, but if I'm going too fast for you, let me know. I don't want to give you too abstract a definition. I'm going to start with a very concrete definition. It's relevant to what we have in the course. Let's just take a point 153. It's in three-dimensional space. X equals 1, y equals 5, z equals 3. We could put a set of coordinate axes here and locate that point. Right now, I'm just going to say it's in there. It's in space someplace, right? And the point 942. Call this point A. Call this point B. And this arrow is going to represent the vector AB. An arrow over the top of it. Make sure we understand that this is a vector. And I'm going to write this vector in three different ways. Maybe more. I could write it as an ordered triple. 8, -1, 1, with an arrow over it. One notation that you'll see. Maybe not in this course. I don't usually use it, but sometimes I do. Okay. Now, does that much make sense? Why 8? Because to get from 1 to 9, you got to go 8 units. You got to go 8 units in the x direction to get from point A to point B. In the y direction, you go from y equals 5 to 4, so you go -1. And +1 to get from 3. Oh, that should be a -1. Almost 54 years I've been doing this, and that's the first mistake I've ever made. Well, yeah. I make a lot of them, so keep an eye on me. Okay, that makes sense? Okay, so that's 8, -1, 1, -1. Or sometimes you'll see this. If you're typing it, it's hard to type an arrow over the top. It's easy to type like a less than and a greater than sign instead of parentheses. So that can occur. My preferred way of writing it is 8 times the I vector -1 times the J vector -1 times the K vector. Anybody unfamiliar with the I, J, and K vectors? Okay. The I vector, okay, let's say here's the x-axis, here's the y-axis, here's the z-axis. The I vector is just a vector of length 1, magnitude 1 in the x direction. The J vector in the y direction. The K vector in the z direction. Okay. So 8i would be a vector 8 times as long as the I vector. So here's 8i. Have length 8, we'd represent it with length 8. 8 times I, and then minus 1 times j. And minus 1 times k. You can then put these vectors together, head to tail. So here's your 8i. I'll do the negative 1k here. And then 1j here. So there's my vector, AB. Now it looks like it's going in this direction here and this direction here, just because I can have my coordinate system rotated any way I want to. Okay, so this coordinate system kind of twisted and turned and everything else to make it look like this. This is what it would look like with a standard coordinate system with the z direction up, and then a right-handed coordinate system with x pointing at you and y 90 degrees in the counterclockwise direction. Okay. So here's our vector AB equals 8i minus j minus k. I won't put the 1 in front of j and k now. Okay. I'll put the 1 here just to make sure we see where it comes from. But there it is. Now this vector can go anywhere. It just can't change direction or length. Okay, so I can apply this vector to any point. So if I apply the vector AB to the point, well, let's pick one. Let's how about the negative 5, 3, 6. Take my AB vector. It has to take me to the point negative 5 plus 8, 3 minus 1, 6 minus 1. Because it moves us 8 units in the x direction, 8 units in the x direction from negative 5, puts us at negative 5 plus 8, which is 3. Negative 1 unit in the y direction, because that's what the vector does. And similarly, in the z direction, well, we get then the point 3, 2, 5. Right there. All right. Okay, well, that's what a vector is like in 3 dimensions, and most of the vectors we talk about in this course are 3-dimensional vectors. Vectors are not always vectors in space. Okay, you can have vectors that have other aspects. You know, vector can be a velocity vector, an acceleration vector. If you have physics, you understand that. Okay, anybody had physics 1? No. Okay, so I could assume that. Okay. Incidentally, if you're going to be an engineer, you're going to have a physics course. Okay. I was a physics major starting my sophomore year. Unlike most physics majors that were in the electromagnetism course, I had had multivariable calculus. And as a result of having had a spinal fusion in the first semester of my freshman year, so I was out for the freshman year, or for the first semester. And that fusion's doing great, almost 60 years old. It's the fusion, not me, I'm a lot older than that. But in the spring, there were only two courses I could really take to fit what I was doing, which is multivariable calculus, which is a no-brainer, you had to get that, and a probability course taught by a guy nobody could understand. And I never understood probability very well, but I made a B. Okay. But I totally nailed. I did all the problems in the book, the multivariable calculus course. So when I got into electromagnetism, I was one of the top 3 students out of maybe 100. Okay. Because I knew the math. All right. All I'm saying then is by having the math that you're getting here and that you've had in your calculus, you're going to be very well prepared not to be stumbling over the math and physics. Okay. It's a big help, big deal. So you have that to look forward to. Okay. Now, where was I? Okay, now let's take another vector. Say let's just say I've got the vector three, 2, 5. This is a point 3, 2, 5. This isn't a vector. This is where this vector takes you from this point. This is now a vector. And that would be a vector from the origin. Here's the origin vector out to this point would be the vector 3i plus 2j plus 5k. Okay. Wouldn't work with this coordinate system because this vector is quite a bit shorter than this one and it would look longer. But anyhow, let's say we take that vector. Okay, so let's see. Now I'm just going to draw it at any angle. It's not an accurate depiction. But this is our vector v equals 3i plus 2j plus 5k. There's some angle between these two vectors. How can you find the angle? Well, at some point in your mathematical background, you should have encountered dot product that you might not have. So how many of you have seen dot product? And most of you, but not all of you. If you had linear algebra, you certainly have. That product is really simple. Now, let's make sure I can still see what I'm writing on the, I wrote a lot of stuff on the board. Well, a little bit of stuff that you can't see, but there it is. Okay, dot product. Dot product of two vectors is the magnitude of one times the magnitude of the other times the cosine of the angle between them. Okay. Now, dot product is really easy to calculate. Just let A1, A2, and A3 be the I, J, and K components of the one vector, and B1, B2, and B3 the I, J, and K components of the other vector. The dot product is A1, A2, sorry, it's easy to do, A1, B1 plus A2, B2 plus A3, B3. The reason that this works and that this is consistent with the definition is the law of cosines, which everybody has encountered in trigonometry. I'm not going to go through the proof using the law of cosines, but it's worth thinking about. Okay, because of the law of cosines, you can calculate the dot product if you know the I, J, and K components of both vectors. Make sense? Easy calculation. Okay, so our vector V dotted with the vector AB is what? I don't have room to write it on that line, but there it is. Now, what's the dot product? You just multiply the I components, multiply the J components, multiply the K components. That's just what this rule tells you. So you got, here's the I, 3 times 8. And 2 times -1. And 5 times -1 again. And that adds up to 17. Well, now we know what the dot product is. This is the magnitude of V, magnitude of W. Think of that as the length and use the Pythagorean theorem. For the components. Okay. The components are 3, 2, and 5. So the Pythagorean theorem tells us that the magnitude of this vector, or the length, if you want to think of it in terms of length, is just what the Pythagorean theorem tells you. Okay. Now, Pythagorean theorem, as you foresee it, is, c squared equals a squared plus b squared. Well, now we've got a squared plus b squared plus c squared. A squared plus b squared would be the diagonal of a rectangle down here, and then you bring it up here and you got another right triangle. Well, I'm not going to explain that. Ask chat to explain to you why, or look it up somewhere. Just Google it. That's 25 and 9, and this is, I think, it gives you 38. Yeah, and the magnitude of AB is the square root of 8 squared plus -1 squared plus -1 squared which is the square root of 66. Well, now we know everything in this equation except the cosine of theta. Meaning we can solve the equation for the cosine of theta. That makes sense? We know what number to put here. Okay, 17. Square root of 38 here, square root of 66 here, and so forth. So $38 times the square root of 66 times the cosine of theta. And you just solve for theta. Theta is going to be the inverse cosine of 17 over the square root of 38 times the square root of 66. 38 times 66 is around 4,000. So that would be like 17 over 20. That's give or take 1 or 2 down there in the 20. Okay. Where's the cosine? Where's the angle if the cosine is 17 over 20? Draw a picture.
Yes.
Radius 20. X equals 17. Right there's the angle. Looks like around 30 degrees. And if that picture isn't familiar to you, make sure you know the circular definition for your trigonometric functions. Something you should know by now, but if you haven't had to think about it for a certain time, and then depending on how many problems you've done that used it, I find that people are often not very well versed on the most fundamental thing in trigonometry, which is that picture. Okay, you lose the forest for the trees. Everybody does. You learn how to do all the manipulations and you forget what's really going on, which is this. So I urge you, is that picture, those who've had physics, is that picture relevant to simple harmonic motion? Simple harmonic motion, the most important motion in the universe? Yeah. Mechanical engineering, aerospace, civil, things vibrant. Okay? You got to know this and understand anything about vibrations. Okay, let's pause for a second. Let me take a breath, figure out what I want to say next. Because this is, okay, assuming that you don't know about dot product, you don't know about cross product, or don't remember it maybe knew it once. I'm going to define cross product for you. Okay. Now this is a different than the definition you're going to get in your text, but I'll also give you that definition, tell you why they work. But this is a way you can always remember to do the cross product, especially if you're not real great with determinants. There we have it. Okay. What do I mean? I cross J equals K. Direction of I is that way, let's say. Direction of J is this way. If I take my fingers and point them in the direction of I and turn them towards J, what's the direction of my thumb? It's toward K. I cross J equals K. Right? Now, I's here, K's here. And I don't have a hand to turn anything towards. So let's say, okay, there's I and J, I and K, right? It's got to be my right hand. Take I, turn it toward J. What's the direction? I turn toward K, sorry. Turn I toward K. I get negative J, don't I? It's easy, isn't it? Okay, so let's tell me what, oh yeah. And if I tried to do I cross I don't have to turn anything. I get zero. But it's not zero the number, it's the zero vector. And that's important. That's why I put an arrow over it. It's not correct to write zero without the arrow, even though you'll see me do it once in a while. Okay, just forget to write that arrow. But you got to keep track of what things are. If it's a vector, you want to keep track of the fact that it's a vector, or you're going to stumble and get yourself confused somewhere. Make sense? Okay. Okay, J cross J, what? No, sorry, let's just do them alphabetically. J cross I. Take a minute and figure it out. At least figure out what J cross I is. Fingers in the direction of J. Turn your palm toward I. Now that's turning toward K. So something's wrong. Let's see. Maybe I'll put my hand like this. That's easier to put like this. My wrist doesn't go that far. Turn I toward J, you get negative K. Okay. Make sure you understand that. Notice also that I cross J is not equal to J cross I. There's no commutative law here. This is an anti-commutative. If you reverse the order of a cross product, you get the negative. It's an important property. A J cross J is a zero vector. J cross J. J cross K is, well, if, now we didn't do J cross J. J cross K is I. Yeah, here's J, here's K, there's I. And then K cross I, well, you can look at I cross K, which is negative J. So this had better be J. Okay. And, well, okay, here we go. K's this way, I's this way. Turn from this direction to this, I get J, right? Okay. And K cross J is negative I. And then K cross K equals zero vector. So let's take a cross product of two vectors. Let's take two I plus 4K crossed with 3I minus 2K. There's a distributive law here. Distributive law of cross product. Okay. Means that this is 2I cross 3J minus 2K plus 4K cross 3J minus 2K, which is 2I cross 3J and 2I times minus, okay, 2I cross 3J plus 2I cross negative 2K. All right, that makes sense? Just simple distributive law. Okay, I've got 2I cross 3J, 2I cross negative 2K. 4K cross 3J, 4K cross negative 2K. You could always draw these things that everybody draws. I did them too, or whatever. Probably drew them wrong. Yeah. Yeah. But operationally, this is what it is. That's visual. That's the real meaning. That's a real law. Okay, this is not a law, that's a convenience. This is the law. You should be able to break these down by the distributive law. Should be easy. Okay, anyhow, then I got plus 4K cross 3J plus 4K cross negative 2K. This equals 2 times 3 is 6, and it's I cross J. In other words, the constants factor out just like they would with algebraic quantities, right? So you can bring the 2 times 3 out here. 2 times negative 2 is negative 4. And we write it out. And then what's I cross J? It's K. What's I cross K? It's negative J. What's K cross J? K cross J is negative I. And if I did everything right, I don't guarantee it, there's your cross product. Now your book will show you a different way to do it with determinants, which is convenient. If you only got 2 components in each vector, this is actually a little quicker. You can skip a lot of those steps once you get used to it. So use whatever's quicker. If you got 3 components of each, you're better off writing out the determinant definition that'll let you read about it. Okay? But this is a perfectly good definition. And then magnitude of V cross W is the magnitude of V times the magnitude of W times the sine of theta, sine of the angle. Okay. And that's consistent. What's the sine of 0? Circular definition. Go to the angle, 0 vector, and see what the y component is at 0. Okay. Something you always you ought to think about when you think about a sine or a cosine. I cross I is 0 because the sine of 0 is 0. Makes the angle 0 with itself, right? Any two of the 3 unit vectors that aren't the same, both have magnitude 1. They're both 1 unit long, if you like. So the product of their magnitudes is going to be 1. And then it's going to be times the sine of theta. Well, when theta is 90 degrees, your y component is 1. Okay. So it all works. It's all nice and consistent. V cross W is perpendicular to V and W. There are 2 vectors perpendicular to any 2 vectors. Got 2 vectors here. Use the right hand to turn one into the other. Right there's your cross product. Okay. It's perpendicular, but so is this. Which one is it? The right hand. Okay. Now, you need to really understand all that. And there's an assignment I was going to give, but I'm going to delay that a little bit. So we have time to bring everybody completely up to speed. You've had linear algebra and everything else. This stuff should be obvious. And if you had physics, we use cross products. So some of you will be a little more conversant with this than others. Still want to do the problems. You want to be really good with these things because they're throughout the course. Okay? It's a vector calculus course. Now, you won't see a whole lot of it after the first couple of chapters because there's a chapter on partial derivatives and stuff like that. It doesn't involve a lot of factors, but then it's heavy. So master this. I'll have the assignment posted by this evening. I want to look through, see just what parts of the text you're going to need. And there's also material and parametric equations and stuff. And some of that seems a little bit. We have to do a little reading. I might wait till Thursday. Actually, I will. We're going to have more time to come Thursday. Whenever we have classes on next week, it's so I guess that'll be the plan.
Okay, so I'll see you tomorrow. Okay, at a halfway.
Okay, any questions?